Okay, so today we're going to look at hypothesis testing with the geometric distribution. That's quite a difficult thing to get your head around, so you might need to look at this video more than once and just sort of kind of go with it. Now, it's okay if you're hopefully if you're finding the geometric distribution okay, then you'll be all right. So let's just recap the geometric distribution. Obviously, the geometric distribution is the number of trials that you have to do until you get a single successful trial, okay? Not to be confused with a negative binomial, which of course is saying that you need 5 successes in however many trials, okay? Right, so when we carry out a hypothesis test for the geometric distribution, obviously, like always, we do 2 hypotheses, our null hypothesis and our alternative hypothesis, okay? Your null hypothesis, as always, is your p-value, whereas obviously if it's the Poisson, it's your lambda value. If it's a binomial, it's your p-value. So in your geometric, it's your p-value that you're assuming to be true, and then your alternative is either it's bigger than, less than, not equal to, etc. Okay. Right, now we need to kind of get this our head around this little sentence so that we're clear with what it is. So if you have a p in a binomial or a lambda in a Poisson, that is different to a geometric, because when you have a geometric p-value, if your p-value is getting bigger, your mean of your geometric is getting smaller, because the formula for E of x is 1 over p. So obviously as this p is increasing, your mean is getting smaller, and vice versa. If this is getting smaller, our mean is getting bigger. Okay? So if you're setting up a hypothesis test to see if the probability of a geometric distribution has increased, you need to see if the test statistic, so whatever you're testing, the number you're testing, falls in the lower end. Okay, whereas if you were testing to see if it decreased, you see if it falls in the higher end. Okay, now hopefully that'll be really obvious as we go through it. Okay, now I'm going to do a couple of examples that I have printed. As we go through these examples, just make sure that you're aware of, you're going to need these formulae, okay? It's much harder to do it on a calculator with geometric distribution. We're going to be using the formulae, so you need to have these written down, okay? I sent you the key points of the geometric and the negative binomial distribution, so hopefully that will help. That should have these formulae on there, okay? Right, so we're going to look at this example here. Well, I'm hoping you can see it okay, which you might not be able to. There we go, I'll put it here to read. So, a company claims that 1 in 8 of their packets of crisps contains a prize. Lee decides to test this claim, and he buys a packet of crisps each day until he finds a prize. That is you thinking, right, this is geometric because I'm doing it until I get a prize. Lee finds a prize ticket for the first time on the 24th day. Test at the 5% significance level when there is any evidence to suggest that the company is overstating the proportion of packets containing a prize. Okay, so let's set up our random variable first of all. So we're going to say x is the number of packets that needs to be opened until finding a prize. Okay, that is the geometric distribution. Okay, so, can't spell prize. Right, then obviously we need to set up our hypothesis. So our null hypothesis is going to be that p is an eighth, because that's what the company claims. Okay, our alternative hypothesis is going to be if they are overstating the proportion, that means we're expecting p to be less than an eighth. Okay, so we think, let's try and get this around our head. So obviously on the 24th day isn't the 8th day, is it? Okay, so that is more than we expect. So as p decreases, the mean increases. Okay, and here obviously our mean has increased, hasn't it? It's more than we're expecting. Okay, so that means that if we're trying to test if p is less than an eighth, we need to consider, hopefully this is making sense, I'm writing it down so you can kind of see it as we go. We need to consider the probability that x is greater than or equal to the observed value. Because as this is decreasing, our mean is increasing. Okay, so now we've got to test whether whether P is bigger than, is bigger than or equal to 24 because it's on the 24th day. Okay, you should set up your geometric distribution. Don't forget to do that. Okay, you'll get a mark for your geometric distribution. You'll get a mark for your hypotheses. You'll get a mark for doing this. Okay, right, now we don't want to use our well, it's not obvious, but we don't want to use our calculator at this point. I mean, you could do, I suppose. Can you do on a calculator? I don't know. Anyway, we are going to use this formula, which hopefully you have got somewhere lodged in the brain. So that obviously is 1 minus an 8th to the power of 23. Okay, and so that obviously is 7/8 to the power of 23. And if you type 7/8 to the power of 23 into your calculator, you hopefully get 0.0464 to 4 decimal places. Okay. We are then using the 5% significance level, so we can draw a little thing. Here's our 5%. Our value is below 5% at 4.64%, which means obviously this is the fail to reject zone. You should be very familiar with hypothesis testing by now, but just if you don't, remind ourselves this is in the rejection zone, so it falls into the rejection zone, so we can say there is sufficient evidence to reject H0 and conclude, and then make sure you put it into context, okay, because if you don't put it into context you lose that last mark. We conclude the company is overstating the proportion, then I'm just sort of copying what they says up here, so the proportion of packets containing a prize ticket. Now hopefully that seems really obvious because obviously 24 is a lot bigger, but yeah, anyway, that's that one done. Okay, right, let's look at example 2. Example 2 is very similar, but just make sure we're happy with it. So, do I need to lift this up again? An electronics company makes small components for use in computers. It claims that the percentage of defective components coming off the production line is 0.05%. The electronics company sells the components to a retailer. The retailer suspects the percentage defective stated by the electronics company should be higher. From a very large consignment recently purchased, the retailer tests the components until he finds a defective component. He finds a defective component on the 90th component that he tests. Is there any evidence to suggest that the retail suspicions are correct? Test at 5%. Okay, so setting up again. X is going to be our number of components tested until finding a defective one. And let's set up our hypotheses. So our hypothesis is, so 0.05% obviously is 0.0005. We've got the right number of noughts? 5% is 0.05. Yeah, that's right. Brain in gear. And then we need to do our alternative hypothesis. So our alternative hypothesis is going to be, we're expecting the retailer company should be higher. So they're saying that it's bigger than, too many zeros, 0.0005. Okay, right, we're assuming that to be true, so our geometric distribution, please don't forget to write in your geometric distribution, okay, because otherwise you're going to lose a mark on that. Okay, so that's our geometric distribution. Now, if we want the percentage to be higher, so if we think this percentage to be higher, we need less goes to find a defective one. Does that make sense? So if we need this to be higher, we need this to be fewer. Okay, so we've got to check, which is like the opposite way around. It's like I just said on the last one. If you've got this, then when you test, you do the less than or equal to. Okay, that's the easy way to remember it. But it does make sense if you think about the fact that the mean is increasing as p is decreasing and vice versa. Okay, so we're going to do that. Now we're going to use the formula for this, which is, hopefully you've got this in your notes. It's in those key points I sent you the other day. So that looks like that. And so this is 1 minus 0.0005 to the power of 90. So that is 1 minus 0.9995 to the power of 90. And then hopefully when you type that into a calculator, it comes up with that. Okay, same thing again, draw your distribution. Here's 0.05. Oh, here's 0.0440. This is interesting that both examples have been like that. That's fine. So then we can say that there is sufficient evidence to reject H0 and conclude the retailer's suspicions are correct. Okay, and then you could put that the electron company should be saying that the percentage defective is higher, blah blah blah. Okay, right, that is hypothesis testing for the geometric. That's quite hard, so try and just take a bit of time to get your head around it. Okay.